All right. Well, thanks, everybody. Just going to try to go quickly through this so we can get to lunch. My name is Jose Daniel Lara. I'm going here to talk about the tool that we use in the National Renewable Energy Laboratory for large-scale problems. And when we mean large-scale, I'm going to start with what is large-scale for us. We start with about 100 million constraints and variables, right? We actually tend to overwhelm Express because Express can only support 1 billion non-zero entries into the A matrix. So when we talk about large scale, we've been working on scaling this problem for a long time. Like the first presentation in Jump Dev that we gave about this was in 2017. Some of the people here were there when we started designing this solution. So very quickly, I work at the Grid Planning Analysis Center. It's basically, it's kind of where we do studies and methodological improvements to do really large grid analysis in the US, especially. Just a very quick intro about why do we care about what we're doing. When we think about planning and studying particularly power systems, right, we're going to have certain problems like Tulipa and others that are going to focus on the build question. What do we build? Then we have to check if whatever the build plan can actually operate, because a lot of build plans that are built usually have approximations of operations, so we don't know if they actually work. So a lot of the presentation today is going to focus on this second box. And of course, once you realize that your plan can build, you have to figure out if it's adequate, if it can actually survive certain events, and then you have to check whether it is stable or not. And to answer all of these questions, we have developed a set of tools that are under the name Sienna. We have Sienna Data, which is a data management tool to create data sets. Anybody who has built large-scale systems we have to combine network data and time series and fuel costs and fuel curves and all of that become very cumbersome, so we have Sienna Data to handle that. We have Sienna Operations, which is the part that we've been using Jump for a long, long time. I think that Oscar has always said that we're the biggest headache because we're the ones who build the largest problems. So a lot of the improvements in performance come when we actually hit limits in Sienna Ops. And then we have a package for Sienna Dynamics where we study electromagnetics, transient stability, and others. Again, Sienna Data, we basically do all of this combination of files to generate very large scale. I'm going to insist on that because that's actually one of the reasons this matters a lot, is that, for example, we're building right now data sets that are nodal for the whole US. So, for example, the study we're going to be talking about today handles this area of the US called the Eastern Interconnection that is probably the largest power system in the world. Just the model itself has over 150,000 buses and 270,000 lines. So it's very hard to get larger than that because this is kind of like all of PGM, all of Florida. So basically you split here, leave Texas out, and leave the West out, is all of these buses and lines on this side, including portions of Canada in the north. So this is kind of what we care about. Right? So a lot of our analyses are going to go from like a planning problem that is zonal, we turn it into nodal systems. And one of the things that you might have seen in the news is how much it matters for these kind of problems, transmissions, right? So I think anybody who's seen the news on the challenges of integrated renewables have seen that we need more and more transmission. So these projects are actually trying to get larger and larger because we need to study more and more value of adding transmission to the system. So when we think about how we model these things, we're going to try to analyze scenarios that look kind of like this, whether we build point-to-point HVDC to connect the whole US, or we build multi-terminal HVDC. And this actually will allow us to bring renewable power from areas that have a load, like in the Midwest or the Southwest, and try to coordinate in the cross-continentally solar and wind. So in this context is where we actually have to build power system models that get extremely big and cumbersome to solve, right? This is why this is one of the fun things about this research is that there is actually not that many methods that allow you to build things and solve it properly, right? We actually have to create new things to actually handle these kind of situations. And like I mentioned, one of the most interesting failures in the process has been the fact that with Jump, we can build these problems, but when we give it to the solvers themselves get overwhelmed. So they cannot do even basic operations like doing an LU decomposition for their process, get into trouble. So, and one of the things that we also realize is that when you're solving large problems, it's not just solving large problems for the sake of it. is what kind of questions open up once you have to solve large problems. And this is the idea of model limited choice. And model limited choice is one of the things that we want to address with this research project. Because when you're solving a grid this big, normally, the default thing that you do is to say, I'm going to build a large unit commitment problem. I'm going to large a large in economic, but that's not how these grids are actually operated. When you get to something that is like this large, this is actually multiple operators. There are multiple agents now trying to coordinate those grids. You're going to have in the whole Eastern Interconnection, you're going to have MISO, SPP, PGM. So just building a large problem, which is like just building a large unit commitment, gives you some ideas about the value of these transmission plans, but it limits what kind of questions you can answer because you're limited by the notion that this is a centralized optimization problem. You don't represent actual operational challenges and actual operational realities of systems this large. So this is not just about how big you are, but it's also what are you actually modeling when you get this large. So just quickly, some of the, these are some slides that I've presented before in previous JUMP devs, but one of the things that PowerSimulations does and Sienna Ops is the fact that we don't have a single model. It's still, actually even people who use like modern programming languages like Pyomo or Jumper, et cetera, they still have like this kind of mentality that you have a model. I actually a lot of times get the question is like, what is the Sienna model? And in reality, what Sienna does and what PowerSimulation does is actually simulate operations. So there's actually multiple operation models. You can have a unit commitment, an economic dispatch, and they can be distinct from each other. You can have merchant models connected to unit commitment models. You can have market-to-market models, which is what we're going to use. And then you concatenate all of these different optimization models into a simulation that you can sequence in different ways. So there is no single model, right? There is no notion of the model, because you configure, depending on what you need, each one of these, and you can configure how you want to model your injection devices, your branches, your network, your services, right? So one of the key differences that we have with other kind of power system simulators like Plexus or Promot or some other ones is like, we don't start from the framework of like, we have this very large optimization problem, you pass 300, 400 parameters, there's one of them that has like 1,500 parameters, and based on the parameters, then you end up with a different thing, right? Actually, these are distinct optimization problems. And we actually exploit a lot of this because we can distinguish between decision models like your unit commitment economic dispatch and your emulation models that are actually, what is the actual operation of the system look like conditional on the decisions taken under a particular forecast, right? So we actually distinguish these two things to say not only what is the result of my unit commitment problem, but like if I made a unit commitment decision given a forecast and then a forecast realizes in a particular way, what is my actual output? So we can do other types of studies like what is your uncertainty cost? What is the effect of a forecast error? What is the effect of an outage? An outage, for example, you can model an outage in the emulator that is not being seen by the decision model and figure out how can the system recover before the next decision. So again, I'm going fast over these slides because these are just kind of like part of how PowerSimulations works. Right, so in a way to think about it is your decision model is like, if I work in NREL, in Golden, and if I want to ski in Vail, the GPS is going to tell me it's about to take you 1.5 hours. This is my forecast of how much time it's going to take me to go. That's my unit commitment. This is what you think is going to happen. And then driving is the emulation, right? So given the route, if I arrive to Silverthorne and there's a crash, maybe I have to take now a different route to get to Vail, right? But by the time that I left work to go to ski, that crash hadn't materialized, so this is still my forecasted route, right? So that's kind of the notions of how we work with PowerSimulations. Again, we go from the notion of a model to the notion of an operational simulator. And we solve really large problems. So we have been working with the parameters piece. I could give a whole talk about the experience of going from the original parameter jump all the way to the existing approaches that we follow. There are issues, discussion between Joaquim, Oscar, and myself for like hundreds of comments trying to optimize the use of parameters so we don't have to rebuild these massive problems, right? The Eastern Interconnection can take up to 30 minutes to build, right? Just because of the sheer number of constraints and variables. So the way that it works is that we have a caching of time series that updates some parameters. This is like, again, kind of parameters in the jump sense. Then we can update the initial conditions where we keep a system state in memory that tells us what is the latest decisions on the latest state of the system. We solve that problem. We write it to a solution in memory before we write to HDFI files. So to Diego's point about how fast can you do all of these reads and writes, the answer is you don't, right? You actually keep a cache, and then you can actually flush that into an HDFI file that has its own memory management. A lot of, I participate in some of the spin-up tools discussions trying to figure out how can you guys operate really large problems. Well, this is kind of the structure that actually handles that, right? When you have to write a billion variables sometimes, with this method, it's like far more effective than actually going to disk immediately. Now, for the purpose of the talk, now, I was mentioning that when you have these very large scale problems, the system doesn't operate centralized. You don't just want to solve a unique commitment problem because there's other operational realities. So I'm going to make the example with only 2 subsystems. So imagine that I'm the whole Eastern Interconnection, and one area is MISO, one area is SPP. Those are two of the largest operators of the US, for those that don't know. And these 2 huge operators actually have some interchanges here. So these 2 operators actually don't solve a joint co-optimization problem. They solve their own individual markets, and they have an interchange. However, in real life, inside of those interchanges, you also have sub-areas. So within MISO, you also have balancing areas, and you have HVDC connected through HVDC and connected to AC. So for example, MISO is connected to a portion of Manitoba Hydro. And Manitoba Hydro is actually split in 2. One part on the north with all of the hydro, one part in the south that is actually connected in situ MISO. So when MISO is clearing its own market, it has to clear inside of this green region and coordinate this interchange with SPP that has to clear its own green region. However, it gets very interesting because in most of the market models, people ignore the transmission. But like I said, the purpose of this model is to understand what happens if we build a lot of more transmission. So on top of having this, you also have synchronous regions. So for those of you who are not into the power system side, you need to actually model the physical balance, not the market balance. So I need to balance on the market sense all of my demand and supply within the green region, but I also need to balance in the physics each one of these red regions. So this red region has to be balanced correctly across an HVDC link because I have asynchronicity here. And then I have to coordinate my interconnection here between the 2 regions, and I need to calculate this interface correctly. Right? I need to actually get very good at calculating what is the real flow between these 2 in AC, considering the whole system looks like this, when I have a combination of HVDCs and so on. The other real-life aspect of these kind of systems is that besides the interchanges, I also have the notion of interfaces. And interfaces are because in very large systems, if you have you need to limit the flow over a group of lines for contingency reasons. Because if a line, let's say if I have an interface here, and this line trips, I can overwhelm this HVDC link. So I have constraints that tell me, beyond my transaction between the 2 markets, I also have to keep a good calculation of what are the flows internal to the regions, because there are limits inside that I need to respect for contingency reasons. So this is pretty complicated, right? Because again, remember, these 2, in real life, this green area and this green area are connected in the physics, but are disjointed in the decision process. So, there's several problems here. Like you need to coordinate congestion management. You need to coordinate the settlement of the auctions if you want to do this. There's also joint market coordination. So for example, one region can actually provide services to the other region to be able to handle situations, for example, when you need congestion relief. And now in real life, you actually have 2 regions that are coordinated but also connected to a 3rd region that is not. So for example, in the Eastern Interconnection, you have MISO SPP that have a lot of coordination, but both of MISO and SPP are connected to another operator called PGM with which they don't coordinate. So we want to find a way to model the coordination between these 2, also conditional on this one not being coordinated, on top of the multi-region, multi-synchronous area, interfaces, interchanges, and HVDC. So because we want to represent what the real operation of these really large-scale problems are. And the most important part here is that if you were to solve this problem as a co-optimization of all of the areas, the challenge is that actually that's the best use of your interconnections, is the best use of your lines. And if you want to justify building new lines and building new corridors to connect these places, you need to represent the existing imperfections such that you can actually derive more value. Because in many ways, what you're going to see here is that given the way things operate, what we needed to capture is the imperfections. So I think that most of the researchers here, when we build an optimization problem, we want to do the optimal thing. A lot of this work is how do we capture the unoptimalities, call it that way, of these systems, right? So, there's different degrees of coordination. You can be completely uncoordinated, and I'm going to show the preliminary results of fully uncoordinated operations. And you can go all the way to co-optimized, right? So you want to figure out something in the middle where you can actually you can exchange information between the two regions to figure out how can they coordinate better. So we use this for benchmarking, and then we use this for benchmarking the other extreme, and we were trying to find the best in between. And in between, we need to coordinate the load, the interchange optimization, the congestion management, and also part of the second year of this project, hopefully for the next jump dev, also how do you coordinate reserve sharing so that spare capacity in one region can be shared across the other one, and you can derive even more value out of your interconnections. But I'm going to skip that part for today. So we're going to present a small formulation. This formulation only is going to focus on the transmission side. So I'm going to simplify all of the generator constraints and whatnot in a feasibility set. So just assume that it could be as complicated as you want. So we essentially have, again, we have system buses, we have synchronous regions, balancing areas. We have our AC lines and HVDC lines. We have the inter-area exchanges, which could be made of AC lines and HVDC lines, or combination of both. You also have the interfaces and the generators, and again, you have the time steps. So this is the indexing. The indexing is pretty nasty. If anybody has an idea how to do this indexing in a better way, I'm more than happy to do it. This is the most creative way of representing this that I could come up with. Because for every one of these lines and regional, we need to have a directionality index to know if the power is flowing from to and to from, right? So is the power from my HVDC line flowing from and to my buses, but also from to my regions, right? Because I need to balance my regions in the energy totals, but I also need to balance my nodes. So I need to keep track of, like, is this HVDC link connected to a particular region or a particular node? Is it connected to a particular area, right? Or because I have to keep track of the three: area, regions, and nodes. And then the same for the lines and the same for the area interchanges, right? So this is kind of like an indexing madness in a way. Like, it gets pretty nasty very quickly. And then I have to subset my generators by the region that I'm at. The generators have to be the branches also. I need to figure out which branches are completely contained inside the region so I don't model them interregionally, and which ones are actually like split between regions. Then, we have some parameters. We have a PTDF for every subnetwork. So this is another challenge. For those going to the general meeting, we have a full paper on just how to handle PTDF calculations for large-scale multi-synchronous region situations. Then we have net demand, generator outputs, and then, of course, all of these kind of devices, inter-area changes and so on, have some flow limits. So it's essentially bounds, right? And the inter-area exchanges usually have bounds in different directions, because operationally the operators work that way. They will define, during these hours of the day, I can transfer this much from here to here and this much in the other direction if I do it to change. A lot of those are kind of like defined by for stability reasons. So like, even though in the physics it doesn't really matter, that's, again, that we have to separate the decision modeling from the physics in reality, right? So we have some expressions and variables. In power simulations, one of the biggest sources of performance is using expressions in jump. For example, we can build in parallel all of the expressions for the flows of the lines. So for systems of this large, we decrease the size, the build times by a lot, because we build the expressions separately and then we just apply inequality constraints. That decreased the build times by 40%, because we can build each one of these. If you have 150,000 buses, and you need to do this one. We don't do this for all of the lines, but you have like 30,000, 40,000 lines. Building each one of these expressions can get really slow, so we speed it up by doing the expressions in parallel and then doing the bounds on the expressions. And then the problem kind of looks like this, where we have a synchronous region. We have to power balance the synchronous region. We have to power balance the areas. The synchronous regions are all of the generation in the region plus and minus the HVDC. Then we have the areas are all the generation and the demand in the area plus and minus the exchanges. And then we have to do the exchanges upper bound. So an exchange can be all of the lines and all of the HVDC lines that participate in the exchanges. And then we have the interfaces, which again is all of the flows on the lines and the HVDC in the interfaces. One thing to note is that while in these constraints, a line can only participate in an exchange. In an interface, a line can participate in multiple interfaces. Right? For example, the Brazilian system has multiple lines that participate in multiple interfaces, but every exchange has a single line, right? And this is kind of like we're implementing this in a package called PowerSimulations decomposition, where we're implementing this logic that you see up here, where we essentially solve a benchmark day-ahead model. We find the commitments and ancillary services requirements. We fix those commitments. And then we basically read the variables from the state, from the region 2 to pass it to region 1 and region 1 to region 2. And this is because one of the most common coordination method that is not coordination at all is that one of the big green circles has a state estimator about what is happening in the other green circle. And the other green circle has a state estimator about the other one, but they're usually off by one time step. So what we can do, what they do essentially is to say, the best view of what I think is happening in the other area is what I thought about it was happening 5 minutes ago, and so on and so forth. So we actually can model that with power simulations because we have this notion of the state. So essentially we solve a day ahead, we solve an hour ahead, and then in the economic dispatch, they solve with the previous information that is stored in the state that behaves like the state estimator. So we can actually even include errors. We can include the forecast errors. We can put a realization so they start screwing up themselves. So for example, here are the interfaces for the different areas. So again, this is a global optimization problem. This is assuming that you can know everything from the day-ahead side. So here you can see, for example, this 1 twin is the interface that is coordinated between the two regions. So you can see it here. Maybe the two reds were not the best choice of color, but it's down here. So you have a constant transfer of about minus 800. So you're transferring power in that direction through the 2 days of simulation. Now when we go to the hour ahead, you can see here that the hour ahead now has some forecast errors. So the 1 twin now is far more variable. Right? It's starting to change because we're saying like we're still in a centralized way, right? We're just kind of refining the process. But when we get to the economic dispatch, because a lot of this coordination happens in the economic dispatch time every 5 minutes, or the miscoordination in a way that what we want to represent, you can see that it went haywire. I actually removed it for a minute because this is the rest of the interfaces, and you can see that there's like significant differences here. Some of these interfaces went to like 2,000 values and so on for one of the regions. And what is happening right now is that we're actually able to represent the fact that the system 1 that cannot optimize globally, but is looking at information that is from the previous step, is making is kind of tracking well the original plan. But the region 2, he has a slack variable because he cannot track very well the other side, so it actually blows, from like 800 all the way to plus 3,000. So we're able to represent the fact that without coordination, one of the areas cannot keep up with the original plan. So what is happening here is that in real life, the error is not this large because this is in a test system, but this is actually what happens in real life. One of the regions tracks kind of correctly, and the other one does pretty bad. And that mismatch in the decision, remember that this is not the physics, right? I want to emphasize that the reason we have 2 values for the same interconnection is because this is the result of the market clearing. Later, then the physics kind of catch up, and there's a process of doing settlements that induces additional costs and whatnot. But what we can see here is that power simulation decomposition captures that kind of behavior, where the view of the systems without sharing information gets like off by a lot. And again, in a test system is more sensitive than in real life because in a test system there's less degrees of freedom. So this lag here kind of like blows up. So in the next step of this work, we're basically testing different testing information approaches, what information can be shared between the systems. We're testing this system that is basically sharing the dual of the copper plate. In the industry, they call it sharing the marginal unit. So it's like a weird thing that New York ISO does with New England ISO in the US, where they share they basically include a virtual generator into their market clearing that is the marginal unit of the previous step. That can be done by just sharing information of the dual. And also the other approach that we've been testing is basically doing a constraint, basically putting a constraint on the flows, given the original plan, and just putting a supply curve of basically constraint violation. So like so you basically say this is a supply cost of doing a constraint violations. You try to basically close this gap, right? And the other option is to also do like another type of benchmarking where you do kind of the best possible coordination, which is an ADMM approach. So you can implement a method that will never be able to work in practice because ADMM is iterative, and in practice you can only solve given information from the previous step. But we can benchmark let's say like best case scenario coordination approach, which is using ADMM, and we can actually do some things like, for example, testing ADMM with one iterations only, just kind of like do one iteration and figure out what is best, or do multiple iterations to see how close we can get with some of these approaches to like a best possible geographic decomposition. That's something that we're trying to test. And then implement an MPI parallel version of this, because if we want to solve this problem at the scale of the system that I showed at the beginning, this cannot be done in a single instance. Thank you very much. This is kind of like our growth in Siena. I think it's been great to be part of the Young community for like all these 7 years, since the original 2017. And you can see how big we've been getting to these days with the approach. So thank you very much. Any questions?